a simple LED is connected with a battery and a switch S. When the switch S is closed, the LED will be turned on. This is very simple, everyone can understand the basic. The battery is B and the positive terminal of the battery is connected to the positive terminal of the LED, and the negative one to the negative terminal of the LED. When switch is closed, the LED will be turned on like this. And this is the very basic principle. Based on this basic principle, a 7-segment display is consisted. Using 7 LED, a 7-segment display SSD is made. And a combination of 7 LEDs is like this. The top one is A and the next one is B, C, D, E, F and G. This is the combination of 7 segments all together, and this will display our digits. When one is on and off the LEDs, and that will be controlled with the controlling circuit, and that will display the shape of our digit from 0 to 9. And each LED has 2 terminals, one is positive and another is negative terminal. It's like this. And one separate LED is just in the right bottom corner, which is for indicating the decimal point. It also has 2 terminals, one is positive and one is negative terminals. I'm gonna group all these positive signals together for easiness to understand, and the ground signal is denoted with a black color, and then all the positive signals are in yellow colored. So I'm considering only the yellow colored as our controlling signal. That will be a output from our controlling circuits. So binary digits are 0 and 1. 0 represent for ground and 1 represents for positive 5 volt. In some case 1 represent for 3.3 volts. Now I'm going to show you how to build a circuit for 4 input binary numbers to its corresponding decimal numbers in SSD. That means in binary input 0000, the decimal will be 0. That means when we input 0000, and the shape will be in the 7-segment display like 0, and accordingly from 0000 to 1001, that's our targeting inputs, and output will be from 0 to 9, the decimal number. Now we have 4 inputs binary and 7 outputs for SSD. I'm going to denote all the inputs as W, X, Y and Z, and all the outputs as A, B, C, D, E, F and Z. With a combination of 7 LED, a 7-segment display is consisted, and that is the reason to call it 7-segment display or SSD. For making our circuits, we need to organize our truth table according to the inputs for our outputs from A to G. So our inputs I have put in the table on the left hand side, and for our outputs I have put all these outputs in the right hand side from A to G. And on the very rightmost side I have put another column for SSD, which will display the shapes of our digits in binary. So for input 0000, we want to output like this. Only the Z will be 0. That means only the Z segment will be off, other than all these segments have to be on. So that time that will be make a shape like this, 0. And the next one, when the input is 0001, the output will make a shape for 1 like this, and accordingly all these inputs and outputs will make a form like this for 2, for 3, for 4, for 5 4 6 4 7 4 8 4 9, and after 9 we actually don't care all the input set and output. That means after 9 we don't want to display anything from for like as a digits. So after 9, or that means after 1001, we don't care anymore which output is outputting in this LED display. So the table is made like that, don't care for after 1001 inputs. So that's why I have crossed all these outputs. That means we are not caring anymore for outputs, which is outputs 0 or 1, we don't care. So after 1001 we don't care anymore outputs, because we have already got our outputs from 0 to 9. So let's move on. All other outputs after x, w, x, y, z equal to 1001 are don't care form. I have put in already in this table. So that's the time. Now we are going to make our desirable combination circuit using logic gates. So for this we need to get the help from the method of Carnap map. That means we need a help to simplify for our output equations, and the Carnap map will help us. Other than that will be very complicated to make equations, and with the logic equations simplifying will be very harder. That's why we just using the method of Carnap map that will make us very simple job for us. For equation A, I have just set up all these zeros and ones in this table, and for input A I have to put the zeros and ones in this Carnap map table like this. For LED A, the Carnap map will be like this. I'm taking the column A. You can see the shaded column is this one for A output, and all these zeros and ones in this table. Yep, I'm putting the 0 first. 0 0 for 0 0 0 1, this is 0, and another 0 is like 1 0 1 0 0 is 0. So accordingly all these ones, like this one, this and this, so all these ones here like this. So I'm gonna describe Carnap map in another videos for now, because the video will be very bigger. So that's why I'm trying to making shorter for now. So all this don't care form I'm putting in this Carnap map like this, x form, like I'm already colored yellow for all this don't care, and then all these ones in the green color, and then all these zeros are in the gray color in this Carnap map. So now time to grouping. So we have to make a group, maximum group of ones. We want to make a group as no ones is just out of this group. All these ones we have to make a group according like 2 4 8 and 16 like this. So I'm making this, the first group is for these ones, because the don't care x we can consider this is as a 1 or this is as a 0. For making our group, as we can consider this is 1, so I'm considering this is 1 1 1 1 1. So we have got a group of 8 sections, and that will output only W. And same for the other. and I have made another group, this one, and this is XZ. I have made another group, and this is outputting Y, and only one is remaining. So for this one I have to make in the corner another groups for this corners one like this, and this will output like X prime and Z prime. Why this is X prime and Z prime? When this is 0 0, all these zeros for the value of X I'm just indicating as the X prime, and then the value for Z of 0 I'm indicating as Z prime. That means when X prime, that means the value of X is 0, and when like only single X, the value of X is 1. So very easy, we have got this equation for A equal to Wx Wy xz plus x prime z prime, and then little bit simplifying we can make the next line Wy x nor z. This is the another logic gate like x nor gate, and x nor equal to xz plus x prime xz prime. Similarly, we have to find out the output equation for B, C, D, E and F. So for LED B, the Karnaugh map will be like this. I'm changing the column from A to B, and then I'm gonna work with the column of B. In this column B, I'm gonna put the output of 0 first, 0 0 in this Karnaugh map, and 1 for all these ones is here, and then all the don't care from is here, similarly like A. And for B we are grouping now. This is the group for B, and this is the rule of Karnaugh map. You can group from the top and bottom, from this side to this side, and corner this corner. I'll tell you that again in our next video how a Karnaugh map works actually. So for now this group will be X prime, and another group for 1 is outputting Y prime Z prime, and this is outputting YZ, and finally we have got this equation for B is X prime plus YZ plus Y prime Z prime, making a little bit simply, and this outputs us like this X prime plus Y, and this circle, inside this circle a dot, it means this is X nor. So X prime plus Y, and then this is the NOR gate, and then Z. So now for C, for all these outputs from C column 0 1s, we have got only one 0 in this column C. This is interesting. So and then after 1 I put this, all this don't care from, it's pretty similar to the other one, and this is the gate. So this is the group for C, and this group we can get this output Y prime. From this group we can get the output Z, and from this group we can get the output X. So finally for C the equation is Y prime plus Z plus X. It's very simple. And for D, from the truth table, the output of all output of D is like this: 0 0 0 and 1s, and all the don't cares. And after grouping we have got this equation: D equal to X prime Z prime plus X prime Y plus Y prime Y Z prime plus W X prime plus X Y prime Z. This is the equation. So for E, this is the Karnaugh map, zeros and ones and don't care form. We put in this Karnaugh map, this is the group, and we can get the equation for E is E equal to Y Z prime plus X prime Z prime. And for F, zeros first, ones don't care, and we are getting like this group, this group, this group, this group, and finally the F is F equal to W plus Y prime Z prime plus X Y prime plus x z prime, and 1 is remaining, which is for g. G is like this: zeros first, ones, all the don't care forms, and this group, this group, this group, this group, and we are getting finally the equation for z equal to z x y prime plus x z prime plus w plus x prime y, and finally we are getting z equal to w plus x z prime plus x XOR y. This is the sign of XOR gate. Inside a circle, a plus circle, plus symbol. So all these equations here for a to g. Now we are going to work with these equations for a, b, c, d, e, f, and g. I'm just drawing a circuit according to this picture, and here we are getting all these inputs. Here is my inputs w, x, y, and z, and remember this line is 1 w when the value is 1 for w, and this line is zeros when the value is 0 for w, because this inverter makes 1 to 0 and makes 0 to 1 when the input is 0, and this will be 1, and when 1 this will be 0. And from the equation, because for a equal to w plus y plus x nor z, so I'm connecting exactly according to the equations. So w already connected to w because w's value is 1, so w. And for y this is going to y plus, this is the x connected to the x NOR gate, and this goes to x. And for z this comes to here for z, and this will go to this OR gate, because all this plus means a OR. So w plus y plus this section is ORed. So for b the circuit is like this, and for c the circuit is like this. For d the circuit is like this. E, f the circuit is like this for g, for equation g, and finally the circuit will be look like this. Here all these connections for a, b, c, d, e, f, and z. Now I'm going to show you how this circuit is working actually in the computer simulation. I'm going to show you in Proteus Simulation how this is working, so you can understand properly how this circuit is actually working. So let's go to see the Proteus simulation first. Let's have a look the Proteus simulation for our circuit. I have got this Proteus program here, and in this Proteus I drawn this circuit according to our equations, and here is the input sections. In this input section I have here w, x, y, and z. So I'm getting this w prime with the help of this inverter, and the switch, this is the switch. You can move to the position to 1 and 0. So all these ones I have connected to the positive 5-volt power supply, and all these zeros I have connected to the ground. So when I move the switch up, that will be connected to 1, and then when I switch it down, it will be connected to 0, like this: 1 0 1 and 0. That's how all this switch is gonna be working: 1 0 1 0. So our 7 segment displays LEDs outputs is here. So this is the our equation A output, equation A, and equation B. This is equation C. This one is D. This is E. This is F, and this is G. So we have 7 equations and 7 circuit we have seen in previously. All these circuits I have implemented in Proteus, and then let's have a look the output. So I'm running this circuit in Proteus. I put the play button on, and in this you can see the output in the 7 segment display. All these 7 segment displays connections are A, B, C, D, E, F, and G, and all this A connected to A, B goes to B, C goes to C, according to this level, each connected to each other. So in this situation, I'm getting the output 0 because our input is like 0 0 0 0. W, X, Y, and Z all are 0. So we can see when 0 0 0 0, our 7 segment display is displaying 0. That means our equation is alright. This is working fine for 0. And we have a look for 1. So I'm changing this one 0 0 0, and I'm changing this one to 1. Wow, this also working. So you can see when the input is 0 0 0 1, we are getting display 1. So that means our equation is alright and the circuit also alright. So accordingly, what about input 1 0 1 0? So 2. Wow, this also working. What about 3? That means 1 1 0 0 1 1. Oh, 1. Wow, it's also working. So looks like everything is fine. What about 4? 0 1 0 1 0 4. Yes, this is the binary 0 1 0 1. That means equivalent decimal is 4. So this circuit also displaying 4. That means our equations and circuit is working. So what about binary 5? That means 0 1 0 1. Wow, this also working. Binary 5. So what about 6 0 1 1 0? Oh, 6, this also working. Nice. What about 7? 7, yes, working. What about 8? 1 0 0 0. Yes, 8 also working. What about 9? 1 0 0 1. Yes, 9. So looks like everything is fine. Our target is like 0 0 0 0 to 0 1 1 0. That means all the decimal numbers from 0 to 9. That was our target, to displaying all the decimal numbers of its inputs, binary numbers. So looks like our binary to decimal converter circuit is working fine.